Hi, Physics 2. Mr. Janowski here. This is part 5, I believe, of the chapter 36 slides. So in the last part, we learned about how to figure out the strength of the magnetic field caused by charge moving through a long wire and different things we can do with that. And we brought back in the I hats and J hats because remember, these are very vector things. So we'll do a little bit more with that idea in this part. And we'll learn another very useful application of electromagnetism. So let's get started with that. So if we're looking at this, we've got wire 1 and wire 2 carrying current to the right. This is actually different than the one we had on that previous slide. So first things first, look at wire 1 and think of the magnetic field caused just by wire 1, and what direction will it point? Will that magnetic field point at points A, B, and C? So this is a right-hand rule kind of thing. So hold out your right hand, put your thumb to the right, and you'll see that your fingers wrap around such that up here, your finger should be coming towards you, so out of the page. If you go below the wire at either points B or C, your fingers should be curling away from you. So those points is going into the page. So this is where it gets different. So now think about what wire 2 is doing. So at which of those points is wire 2's and current 2's magnetic field going to increase or going to decrease the magnetic field by wire 1? So basically, again, to do this kind of thing, think about where does wire 2's magnetic field agree with or disagree with the magnetic field of wire 1. So right-hand rule again. At point A, should also be pointing out of the page. So that would increase it. At point B, wire 2 is going to be pointing out of the page, but wire 1 is going to be pointing, its magnetic field is going to be pointing into the page. So there it's going to decrease it. And then at point C, this point is beneath both wires and both have current going in the same direction. So at both of these, the magnetic field will be going into the page, so that one should increase it. So there are your answers. So what is our formula for the magnetic field around a current carrying wire? Check your memory, see if you can remember. Yeah, it's this one. V is equal to mu sub naught I divided by 2 pi r. So mu sub naught, again, is that constant, the permeability of free space. This is a constant of the universe. I is the current, and r is the distance from the wire in meters. So when does this formula hold? This works when L, the length of the wire, is much bigger than the radius. Not the radius of the wire itself, but the distance away from the wire that you are. So if this wire is a meter long, you can use this formula if you're a few centimeters away, but if you're talking, 50 centimeters away, it's not going to be very accurate. So you've got to be fairly close to the wire for this thing to work. So here we go. We've got 2 wires. This time the current is going in opposite directions. So we know the lengths of these wires, we know how their separation, and we know the current. So we're going to try to figure out what is the force that each wire is exerting on the other one. So first we've got to figure out the magnetic fields caused by each of the wires. We need to figure out their directions and their magnitudes. So think about the directions. How are we going to figure out the direction of the magnetic fields? This is going to be the grip rule. So if you're looking at that top wire, thumb goes to the right, fingers curl around. So beneath the top wire, which is where the second wire is, your fingers should be going into the page. Now do the grip rule for the lower wire, the bottom wire here. So now your thumb is pointing to the left. So above that wire, which is where wire 1 is, your fingers should be going into the page. So how do we figure out the magnitude? Well, that's the formula we just talked about. This is the one we learned in the last part. So how can we determine each force's direction? So the grip rule gave us the direction of the magnetic field. What rule gives us the direction of the forces? Yeah, the cross product rule. And how can we figure out the magnitude? Well, this is a formula we had before. So the first part of this, doing the grip rule, wire 1 is going to cause a magnetic field, which we're going to call B1, into the page along wire 2. and wire 2 is going to cause a magnetic field B2 into the page along wire 1. And then you plug your values into this formula here, and you get 283 microteslas. So a fairly small magnetic field. Now, how do we figure out the force? You do the cross product rule. So B2, the magnetic field caused by wire 2, is going into the page at wire 1. So your finger should be pointing into the page, but which way is wire 1 going? Which way is current 1 going? It's going to the right. So your fingers are pointing into the page, and your thumb should be pointing to the right. So you should be looking with your palm facing up. So yeah, the force on wire 1 is going to be up. So do the same kind of thing at the bottom one. So B1, also curving into the page. This time your current, so your fingers should be going into the page, and your current is going to the left. So now your thumb is pointing to the left. And which way is your palm facing? Your palm is facing down. So one is pushing, the bottom wire is pushing the top one up, and the top one is pushing the bottom one down. So these wires are actually going to repel each other. And then to figure out the magnitude, just grab the right formula and plug and chug. Put it into things. The angle we have here is 90 degrees. So again, the angle in this case is the angle between the magnetic field, which in both cases is into the page, and the length of the wire and the current. And those directions are side to side, so it will be 90 degrees. So you get a very small force, 902 micronewtons. So 902 times 10 to the minus 6 newtons. So remember, we did this before. You've got this situation, we've got one loop. You can see which way the current's going. So use your right-hand rule and figure out the direction of the magnetic field, especially within the loop. So you should be holding your right hand in front of you and tracing out the way the current's going to go. And hopefully by doing so, you can see that the current's going to be going left to right through that loop. So if instead of having a single loop, what happens if we took this piece of wire and wrapped it around many times? So in this picture, you can see, sorry, it doesn't match exactly what's going on in these pictures. I looked, I couldn't find one. So you can see the current coming down here. So coming down in the front, going up in the back, down in the front, up in the back, down in the front. I'm not going to do it for every loop, but that's the idea. Down in the front and up in the back. So what do you think is going to happen with the magnetic field if we have this arrangement? You're going to get a lot of magnetic field because what you've just built is called a solenoid. So a solenoid is a long wire consisting of many loops, although we're usually going to call them turns. So these are turns. So in this picture here, I added this to the picture. You can see this is not magnetic field. This is the current is coming towards us. And down here, the current is going away from us. So current coming down. At the bottom of this solenoid, it's going away from us, so you're looking at the tail feathers. At the top of the solenoid, it's coming towards us, so you're looking at the point of the arrow. So yeah, this is a solenoid, and you can get very big magnetic fields because you can have lots and lots of loops. So each loop just kind of adds, I'm calling them loops, I should be calling them turns. You can have lots and lots of turns. So each of the turns is just adding more magnetic field to this area in between. So notice if you were to compare the magnetic field created by the solenoid to the magnetic field of just a bar magnet, it's going to look really similar. The solenoid basically acts just like a bar magnet. So above and below the solenoid, so let's just focus on above here, you're not going to have a lot of magnetic field, which you can tell because there just aren't many lines up here. Remember, the density of your lines tells you the strength of the magnetic field. And the reason that is because the contribution of, say, let's just look at this guy right here. So this is coming towards us, so do the grip rule. So you should be pointing your thumb towards you. And above that point, yeah, you've got it going this way to the left. But the contribution of this guy is going to be largely canceled out, not completely, but largely canceled out by this guy. So this guy is beneath us, and if you're doing the right-hand rule, you're pointing your thumb away from you. So the contribution of this guy here, up here, is going away. Now this guy is further away from this point than this guy is, which means this point up here is going to have more of an influence, but this one kind of largely cancels the other one. Not completely, but it largely does. So you don't have very much magnetic field outside of the solenoid, but you do have a lot inside the solenoid because here everything's contribution is just agreeing with each other. So we've got this formula here. This gives us the strength of the magnetic field in a solenoid. So B again is your magnetic field. Mu sub naught is the permeability of free space. I is your current. N is the number of turns. And N is just dimensionless. This is just a number. This is how many turns there are in your loop. And all this gets divided by L. So yeah, L's and I's kind of look similar. Lowercase L's look like capital I's, and they look like ones. Not my fault. But yeah, L is the length of your solenoid. So that's what the things mean in that formula. So you might get a math problem where you just need to know what everything is, plug it in, you get your answer. Or you might get one of these guys. You get a ratio problem. So we're going to compare two different solenoids. Solenoid 1 is 3 times as long, has 4 times as many turns, and carries 5 times the current of solenoid 2. How do their magnetic fields compare? So let's start with step What are we trying to figure out here? We are trying to figure out the ratio of the magnetic field of solenoid 1, so B1, to the magnetic field of solenoid 2, B2. And so we need to, if you get one of these ratio problems, you want to make a list of the things that you know. So I've made my list in the same order in which I've given you the information. So let's see. Solenoid 1 is 3 times as long as solenoid 2. It has 4 times as many turns, and it carries 5 times the current as solenoid 2. So your numbers are going to be 3, 4, and 5. So do each of these numbers go on the left or the right? Well, in this case, they're all going to go on the right. So yeah, solenoid 1 is 3 times as long. So L1 is equal to 3 times L2. 4 times as many turns. So N1 is equal to 4 times N2 and 5 times the current. I1 is equal to 5 I2. So where do we go from here? Go back to this B1 over B2 idea and make that equal to something over something. And then you make the top thing equal to the top thing and the bottom thing equal to the bottom thing. So we've got this. Unfortunately, we have this unfortunate situation where we have a fraction being divided by a fraction, which is just awful. So we should deal with that. So one thing we can do is mu sub naught and mu sub naught, they just cancel. The i's and the n's stay put. They're where they belong. The l's change places. So L1 on the bottom of the top goes to the top on the bottom, and L2 on the bottom of the bottom goes to the top of the top. So hopefully that makes sense. And then from there, you go back and you either keep or replace all of the things. So we end up replacing all of the solenoid 1 things with their solenoid 2 equivalents. So you plug all of those guys in, and then lots of things are going to cancel. The only things, in fact, that don't cancel are the 5 times 4 divided by 3. So you get 20 over 3, which ends up being 16 and 2/3. So yeah, ratio problems. They're not that bad. So another thing we can do with these solenoids is you can take a piece of iron, so it could be a nail, it could be a cylinder of iron, it could be anything of iron, or any other ferromagnetic material, ferro meaning iron. I'm not going to go into what ferromagnetism is. You place it inside the solenoid, and now you have created an electromagnet. So in these two images, they're kind of busy images, there's a lot going on. The top one is just a solenoid, which we're going to say has an air core, meaning the only thing inside the solenoid is just air. I know it definitely looks like there's something here, but there's really not. Yeah, so this is just an air core. The bottom one is going to be an iron core. So if you look carefully, you'll notice, even though there's lots of lines here, there are a lot more lines down here. So when you put an iron core inside of the solenoid, you can really increase the strength of the magnetic field. In fact, you can do it by hundreds of times, the strength of the magnetic field of just having an air core solenoid. Solenoid, solenoid, whichever way you want to say it. So, yeah, when you do this, you have created what's called an electromagnet. So electromagnets have many, many uses. So, yeah, here's a solenoid, but we put an iron core in it. So now this is an electromagnet. You can use electromagnets to ring like an alarm bell like this. Doorbells can also be made to work this way. You can obviously lift pieces of metal. You can erase magnetic hard drives if you want to. Some of you will get that reference there. And over here, this is what's called a relay. This is a way of getting a magnet to work a switch. So the basic idea is In the situation right now, common terminal, okay, so you would have current coming up through here, and it would go up through this contact and down through here. And this bottom one is doing nothing at the moment because this little arm here, well, armature is what they're calling it, is being held in place by this spring. So yeah, the spring is holding this up next to this one. So if we were to pass a current through here, through this solenoid, and now that we have a core in there, it's technically an electromagnet, this is going to create a magnetic field that's going to pull this down here. So this is going to defeat this spring, and it's going to smack this thing from up here down to down here. So if this thing were to move down, your current would be going up around here, down through there, and through here. So it's called a relay. It's kind of an old-fashioned way of electrically throwing a switch, or electromagnetically throwing a switch. So yeah, that's what a relay is. Circuit breakers can also work the same way too. If you have enough current going through the thing, it pulls on the armature and takes the contact away from where it needs to be. So another application of these is one you're using right now. If you're watching this video, you're listening to a speaker. Either you're listening on a laptop or you're listening on your phone or you've got your earbuds in. All of these things have speakers. So the way a speaker works, basically, let's look at this simple one first. So you've got this cone here, which is made of cardboard or paper or something like that. And the cone is attached to an electromagnet like this. And right behind this electromagnet, we have a permanent magnet like this. So what you do is you send an electric signal going through these wires. So on this picture, so the signal is going to go through here. Once you have current going through here and making a magnetic field, and you've got this iron core in here, which strengthens the magnetic field, you now have a magnetic field that's going to interact with the magnetic field of this one. So the signal you're sending through here is going to be analogous. It's going to be analog. If you're hearing sound, it is analog to the sound wave that originally made that signal. Sorry. So this electrical signal, let me restate that. This electrical signal is analogous to the sound wave, which is waves of air vibrations, changes in air pressure. The electrical signal is analogous to that sound wave, and it goes through the coil. So here's just an example of a sound wave. So this is going up and down at, not one clean frequency. This is, a mix of frequencies. It has this current going through and, going up, pushing the current one way, going down, pulling it the other way. It changes the magnetic field being created by this. So at some points, it's going to be a magnetic field that draws this guy back, which kind of pulls the air in the cone back towards the speaker, called rarefication, or it will repel and will push the speaker cone forward. So that increases the air pressure. So yeah, that's how a speaker works, whether it's an actual speaker or whether it's an earbud or anything like that. Microphones work kind of the same way, but there's another trick going on called induction, which we'll learn next chapter. But so we're not ready for microphones, but yeah, it may seem like microphones are kind of the opposites of speakers. They actually very much are. So another use of these electromagnets is an electric motor, which we use all of the time. But this video is getting long enough, so we're just going to save electric motors to next time. They're important enough. They kind of warrant their own separate part of the slides. So to review, just back to this problem. How are we going to figure out the magnetic field, each magnetic field's direction and its magnitude? We will figure out the direction using the grip rule. So apply that right-hand rule to the current going through each of these wires to figure out the direction of the magnetic field. And to get the magnitude, you use this formula, which we learned last time. So these magnetic fields are going to interact with these currents, causing forces. So how can we determine each force's direction? We'll use the other right-hand rule, the cross product rule, to figure out the directions. And the magnitudes, we'll use this formula. F is equal to ILB sine theta. So what is it called when you have a long wire with many turns? Some people would call them loops. You should call them turns. These things are called solenoids. And here's your formula for the magnetic field created by a solenoid. So B is equal to mu sub naught, this constant, the permeability of free space, times I, the current going through the solenoid, times N, the number of turns in the solenoid, divided by L, And this is not L sub S. I just realized it looks like that. Yeah, this is L, the length of the solenoid, and this S is part of the picture. I'll change the slides. I'll move this guy over a little bit, but too late to change the video. And what is it called when you put an iron core inside of a solenoid? What do you get? You get an electromagnet, which has very many uses. So that's it for this part of the slides. Hopefully you guys found that helpful.